So let us start today with an example. This example, in fact, is taken from the midterm exam of last year. So it'll give you an idea of the level of difficulty. So please read this through and attempt it just for 1 minute on your notebook. A drop of water at 20 degrees Celsius. Just take notes of the basic numbers. You don't have to write the whole thing down because I will post it on a PDF file on Blackboard for you. But take just the basic numbers that you need. Drop of water at 20 degrees Celsius is forming under a solid surface. The configuration just before separating and falling as a drop is shown in the sketch. Assume the forming drop has the volume of a hemisphere. That's the shape of the drop. What is the diameter of the hemisphere just before separating? Now recall that in the exam you will have access to your notes and your books. It's open, it's an open book exam. So you can, of course, look up your fluid properties. It makes it easier if you've prepared a little bit, a little sheet with the most used properties. And if you know as well where everything is in your book, or have perhaps printed out from the internet some sheet with properties, and you're ready to go. So those are tips to do better on the exam. You can prepare your material and bring it to the exam. You can use any material that you have, past homeworks that have been returned to you, graded, extra exercises that you have done on your own. You can bring that as well, lecture notes, and the book, everything, whatever book you have. Okay, so what would we have here? We have, well, it's water, so we look up the properties of water. And what forces do you think we need to consider here? Yes? Gravity? Very good. Surface tension. Gravity and surface tension. So we look up the specific weight. Yes, very good. I have it right here, so we save a little time today, but you would have to look this up. In fact, this number you could even get to learn by heart. The specific gravity of water at standard conditions. It's 9,790 Newton per cubic meter. And the specific, the surface tension, 0.073 Newton divided by meter. Remember, is force per unit length. And this is at 20 degrees Celsius. Okay, so we have all our properties that we need. What do we need to do next? Any suggestions? Yes? Excellent. Free body diagram. What forces do we have? This, let's see, I guess this drawing might cause you to be confused a little bit, but remember that the force, what's the other force we have? Weight. So weight points downwards. So what we need from the surface tension is a force that is opposite the weight, right? So don't be confused by this little picture and realize that you're being told that this has the volume of a hemisphere. So really what we want is an opposite force in the other direction, right? Because otherwise we couldn't, hold the weight. So that's going to be our surface tension here. Sigma times a length to get a force. And this guy is the weight. So the key is to do a free body diagram and do equilibrium of forces. And equilibrium is simply that the weight of the drop must be equal to the force due to surface tension. For the weight of the drop we have, well, it's the half of a sphere, so we calculate the volume of a sphere divided by 2 and multiply by the specific gravity. So the weight would be so pi d squared over 12 and cube. This is a cube, this volume. Let me erase this guy, it's a mistake. Cube. You of course can have tables of volumes of things like that in your book. They're available in case you forget. This is a cube multiplied by the specific weight. Now the key here is to get your surface tension force correctly. So, what is the line of action of that surface tension? Very good. The circumference. So it's pi times the diameter, the circumference, we have the diameter here, times surface tension. Everybody clear there? Any questions? Does it make sense to you? Yes? That's right. But where is the circumference being applied? It's over here. So it's the same for the half circumference as if you look, I mean, it's right here, right? This is, if I sort of draw it in perspective, is this circumference right here. What do we do now? What do we do now? We're looking for D. So, solve for D. Yes, we're ready, right? We solve for D. Okay, so one of the D cancels out, and I have D squared. Let me just go a little bit quicker here. And this is 12 times, we have surface tension 0.073. Remember how to do better in your exams? Carry your units, okay? Just to make sure that everything is correct, we carry our units all the way. 9790 newtons per cubic meter. And sure enough, this will cancel out the newtons, cancels out 1 meter and gives me a meter squared, which is correct for the diameter. We can put now these numbers in a calculator. Of course, you're allowed to use a calculator during your exams as well. What you're not allowed to use is your phone. But of course, that's obvious. 10 to the minus 5 meters squared. And you can now take your square root and get diameter equals, I've already done this, of course, to make it easier. Or 9.46 millimeters. Now, if you had made a mistake with your units, you always remember what I've said before also about doing better in your exams. Always expect and inspect. So you expect this result to be like in the order of millimeters. Maybe, 9 millimeters might sound a little big, but it's okay. It's in the order of what you might expect. It's a drop, okay, it makes sense. If it had been something like 2 meters, okay, it's obviously wrong somewhere. And the reason I say this is because indeed we did have, I believe, when I had quite a chuckle when I saw a 10-meter diameter drop on one of the exams. And so inspect and learn to use your, yes, that was quite funny, 10 meters, a huge, gigantic drop. And so there was some sort of mistake, of course, with some of the numbers used and so on. So be careful, okay? Always look at your answer and just think for 1 minute. Does it make sense? And yes?
So is it always going to be the case, like right before separating, like for a fluid attached to like the surface at the bottom, like right before separating, is it always going to take like this?
It's a simplification that we're making here, but it's a simplification that makes sense because in really what happens is contact lines, like we saw in some of the movies last class, the contact lines travel, you know, and perhaps the drop will slowly, you know, detach, and the circumference will be smaller. But if the circumference is being made smaller, you can see that the surface tension force is going to be smaller and smaller, so it'll detach just more quick. I mean, it's just simply, there's no way to recover from that situation once this situation is reached, that the surface tension is not able to balance out the weight, then it'll only continue. It's a situation that, because you can imagine that the diameter of the drop will grow up to this point, perhaps also the volume of water there is growing. So if the balance is broken somehow, the drop will detach. So this is the maximum diameter it will reach, despite the fact that as it detaches, it might change shape, right? You see? So it makes sense in that way as well, if you think about the whole process a little bit. Although we made some simplifications, they do make sense. So you can see from this exercise that what we expect in the exam is just a fair application of your basic concepts, correct usage of units, and careful solution of simple equations like this. This is what you can expect. And we will go over other examples from previous exam as we cover the material as well for your confidence, and put the exam online on Blackboard for you to see from the previous years. And so practicing with some similar examples will prepare you well. Okay? So now we can start a new section, which is going to be the section on statics. And the basic premise of this whole section on fluid statics is that, of course, the fluid is at rest. The word static should reveal that. And if the fluid is at rest, there can be no shear because there's no flowing. Remember, shear is associated with flowing, right? A definition of a fluid is that it will deform continuously under the effect of a shear stress. If it's not flowing, it's not deforming, there's no shear. If there's no shear, there is no viscous forces. That's the basic premise. And so if there are no viscous forces, the only force that is at play is the forces due to pressure. Of course, weight as well. But the only surface forces are those due to pressure. And pressure, as drawn in this little cartoon, so the things to remember about pressure, basic things, are that it always acts normal to every surface, perpendicular, I mean. And the only force acting is fluid weight, the only other force. So we apply Newton's laws, just a force balance to obtain we look at this picture and we imagine axis here, x, so I think this one has to be x if I draw it this way, y, z, okay, z in the vertical direction, and we see that there are only pressure forces on the x and y direction. The weight only acts in the z direction in my axis, so that means that in directions x and y there can be no changes in pressure because pressure has to balance out, right? So we can see that dp dx is equal to 0 and dp dy is equal to 0. Pressure basically is acting on every surface of this small little volume equally on all the vertical faces. It is only on the horizontal faces where we can see that there needs to be a change in the pressure between the top and the bottom face so that we could have something balancing out the weight. And so the weight of this small cube is weight per unit volume is equal to the change in pressure in the vertical direction, and that weight per unit volume is rho g. And the minus sign is just indicating that pressure, of course, increases downward in the fluid, and that is something that you might find reasonable. As you go deeper in the ocean, the pressure is going to be higher and higher, so pressure increases downward. And this is going to be our basic equation for this chapter. It's called the hydrostatic equation. So just remember, pressure increases downward. For an incompressible fluid, rho is equal to a constant. It doesn't necessarily have to be a constant. Rho could be a function of also z, in which case we would have to integrate, and you will see that next class. But if the flow is incompressible, then rho is a constant, and then we simply have delta P is equal to minus rho G delta Z, or rho GH if H is measured downward. So we can get rid of that minus sign and think of H measured downward from the surface of the water, say. Rho GH or gamma H would be the case for an incompressible fluid. So the pressure depends only on depth. And also pressure is isotropic. It acts equally in all directions. Isotropic, yes. There's actually small derivation that one can go over to prove that pressure acts equally in all directions, but I have decided not to do this in class, and because it's a little bit of a 10-minute derivation of if I do it on the board, and for some of you that are mathematically inclined, I will put a short video. I call them the sort of supplementary theory videos that I have picked up from previous recordings of lectures in the past, and can put online for you if you're so inclined and you want to really understand and be, see a mathematical proof of what I've just said. You can see it there. But for many of you, it is perhaps satisfactory because it makes some, it makes physical sense, and you're happy with this more physical approach. So, for those of you who are interested, then see the theory video that will be posted to go with this lecture. It's only 8 minutes and 40 seconds, and it's just one slide going over the derivation that proves this point over here. Somebody had a question, but I'm sorry. Did you have? Okay, you're okay now? Okay. Sorry, I just was finishing my idea. Okay. Okay, let me go back here because I have something more to say. You can also write, I just didn't leave enough space, so you can also write delta P. Still, we're talking about a incompressible fluid, so rho is equal to a constant, so we have delta P, say P1 minus P2 equals gamma H. This is rho G here, gamma. And so this is with H equals Z2 minus Z1. So if we have a situation of a fluid, water, say, the surface of the water, usually when we draw in engineering pictures, sketches that indicate a surface of an interface between, say, air and water, we use this little triangle. This little triangle just indicates that this is a surface and it's under atmospheric pressure, like, the surface of the ocean or the surface of a tank. That's all it means. Okay? So this is water here, and at the top there would be air. So we are measuring Z comes, in our coordinate system is measured from the bottom up. So say we'd have, this would be Z1, and this would be Z2, and the difference between the two is H. And this is for our coordinate system that we drew previously as well. There. Now, notice that from this way of looking at the equations, we can actually write H as a function of the difference in pressure, P1 minus P2 over gamma. You see that? I'm simply rearranging things a little bit. So this is interesting, and it's very useful in engineering. It means that the pressure difference between 2 points can be associated with a height of a liquid, associated to the height H that I've drawn here. And this is quite useful, and it's going to be used in the measurement of pressure. Often we use the height of a column of liquid. You will see that also in your laboratories quite a lot for this class. So we use a term in engineering which is called, is the pressure head. And this is simply the height of a column of liquid of specific weight gamma, required to give a pressure difference delta P. So we will use this concept quite often in this class, and you'll see it often in the future as well. when we talk about pressure head, or often we just say head, what is the head between these 2 points? Okay, in, say, a piping system or different tanks, or perhaps from the bottom of a, say you have a turbine at the bottom of some sort of mountain where you have collected some water and pipe it through a turbine to generate hydroelectric power, for example. It is often that we talk about the head as it is as a measure of pressure. It just is. So what you need to be careful is that even though we're really talking about pressure, the dimensions of head are length because it's a height. It's just that it's the height of a column of liquid which is equivalent to a pressure difference. And it's by a certain tradition in engineering that it has become common usage, and so you need to be aware. Okay? How do we use this, for example? To measure pressure, we can use columns of liquid. The classic is the mercury barometer. We'll see a few examples. The mercury barometer is simply an upside-down tube filled with mercury that is, well, the bottom of this tube is open to a pool of mercury, and the top side of this tube is closed. So here it says vacuum once again. Here it says vacuum, but really it's not vacuum. It's like there's vapor there. There's the vapor of the mercury itself in equilibrium with the mercury. So it's vapor. There's vapor pressure, to be correct. Okay, but you know, sometimes one wants to be simple. So there's vapor pressure here, really, rather than vacuum. We use this device, a tube filled with mercury, turned upside down in a pool of mercury, and the column will come to an equilibrium position. Depending on the pressure, because we have pressure here. Let me just draw this as a sketch so it will be easier. We have the tube and we have the pool, and so we have, say, the mercury here. I'm drawing the contact angle here. Remember that the mercury has a non-wetting contact angle we saw last class. And so over here we only have pressure, atmospheric pressure. And here this column has some weight. So the equilibrium is going to be the weight of that column of fluid balancing the pressure. And so this equilibrium position is due to the balance of forces between atmospheric pressure and the weight of the column inside here. And we, of course, neglect any pressure forces in this little space over here because, like I said, it's almost vacuum. It really is the vapor pressure, but it's very, very small. So we neglect that and we write the atmospheric pressure is equal to gamma H. Simple as that. For example, atmospheric, here it is, there's a value for the standard atmosphere. It's about 760 millimeters of mercury, or 29 inches. 29.92 is the measure of atmospheric pressure at standard atmospheric conditions. Sea level, 20 degrees. Now, the reason that we use mercury is because the value of gamma is such that we get a nice, manageable column of liquid to measure the pressure. If we were to use water instead, do you have any idea of what would be that height of that? It's 10 meters. Yes, it's 10 meters. So of course it would be a little bit unmanageable to have a glass column of 10 meters height. So that's why mercury is preferred. Somebody had a question? Did you have a question? No? I saw a hand. Sorry, and I didn't mean to ignore you. I was finishing a sentence. Okay, good. So this is one application of this simple equation to measure pressure, atmospheric pressure. There are a variety of other manometers. We call manometers basically these devices that use a column of liquid to measure pressure. Those are manometers. Okay, number 2 is called a piezometer. Piezometer is used to measure pressures which may be, pressure, for example, inside a tank. I've drawn this little circle, but it could be a big tank containing some sort of liquid. And you just, in a big tank that contains, say, gasoline or water, of course, you can, at the point where you want to measure the pressure, just have a little hole and a tube, and vertically upwards, connected to the atmosphere. That height will indicate the pressure. This is called a piezometer, a simple tube open at the top. So what we have is at this position, A, let's call it A, and we want to measure the pressure at A, and the height of this column indicates that pressure. In a container, simply gamma H again. Now, one thing to notice. Remember the difference that we made between between absolute and gauge pressure, right? Remember that? We made a distinction? Okay, what pressure are we measuring here? This is open to the atmosphere, so atmospheric pressure is acting there. So atmospheric pressure is acting there, and the other pressure is acting against it, and we're measuring this difference in pressure just as gamma H, the column of liquid, and basically we've ignored the fact that there's atmospheric pressure there because this is actually a relative pressure with respect to atmospheric, which we call gauge pressure. So this is useful to measure pressures which are just slightly higher than atmospheric. First, tanks containing liquids, of course. If the gray material that I've drawn in the tank here was a gas, this is not going to work, right? The gas will just escape through the open tube. So this is for tanks containing liquids. Okay, then we have this is the piezometer. Then we have what's called the U-tube manometer, and you're going to use this quite a bit. I said the previous one was only useful if you had liquids, because otherwise they would escape. This one, now we can use it for gases, because we can have a gas in here, but there's a column of a different fluid here that is a liquid, the manometer liquid, that is the light blue here in this cartoon. And so there's something in here that's called the gauge liquid that is different from the liquid in the tank. So now, again, we want to measure the pressure inside the tank. So say this is point A. So let's call this 1, which is at the same height as point A in the tank. Let's call this one point 2. And so you first see that there's one column of liquid here, one distance. Let's call this H1. Now in the blue liquid, remember, in the same liquid at the same height, there's always the same pressure, because pressure only depends on height or depth, right? So these 2 points 2 and 3 are at the same height, therefore there must be the same pressure. So 3. So immediately we see from here P2 is equal to P3. They're at the same height, same fluid, same pressure. But up here we have atmospheric pressure, so we have another point, and let's call this H2. The tube is open here. And now this can be used for a gas. Can be used to measure pressure in a tank containing a gas. So the pressure at point A is the same as at point 1. Pressure at A is equal to pressure at 1. Pressure from 1 to 2, we have a pressure increase, right? So from 1 to 2, we have a pressure increase of gamma 1 H1, where gamma 1 is, this is the liquid in here, gamma 1, and this is, here is going to be gamma 2. There's two fluids. This one could be a gas as well. So gamma 1 H1 is the difference in pressure between points 1 and 2. Yes? That makes sense? Okay. We saw that 2 and 3 are the same fluid, same pressure, sorry, same fluid, same depth, same pressure. And so from 3 to atmosphere, we have that, well, now we're going upwards, so pressure decreases. By gamma 2 H2. So we want to measure the pressure at A. Pressure at A, 2.2, increases by gamma 1 H1. And then I can do pressure at 2 is equal to pressure at 3. So pressure at 2 is pressure at A plus gamma 1 H1, and pressure at 3 is equal to, well, we're going to measure just gauge, and so it's gamma 2 H2. Atmospheric pressure we don't need it because we're going to measure gauge pressure relative to atmosphere. So now we can solve for PA, and it's simply going to be equal to gamma 2 H2 minus gamma 1 H1. Now, it could happen that the fluid here, if it's a gas, then perhaps gamma 1 is much smaller than gamma 2, and then we can neglect that other term and write PA is approximately equal to gamma 2 H2. And this tube, now this U-tube, becomes a very useful device, and you will use this quite a lot in your laboratories. Depending on what the expected pressure in the tank is, you might choose to use a different gauge fluid. It might be water. Water might be appropriate. It might be, mercury or something else, depending on how much pressure you expect to finding point A. Make sense? So I have two more examples of manometers to see, and then we will take a little break, and I'll give you an announcement as well for next class. So just bear with me with two more examples. This one is a U-tube, the same as before. The only difference is that we have the U-tube connecting two tanks instead of being connected to the atmosphere. So we sort of know what we're going to have to do. We have point A. We want to measure the pressure difference between point A and point B. We see that point A is at a height 1. This point here is at a height 2, which is equal to this point 3. And we have, again as before, H1. And here we have H2. We see from here immediately that P2 has to be equal to P3. Same fluid, same elevation equals same pressure. And P at point A is equal to P at point 1 because, again, same fluid, same elevation. Point 2, we need to increase pressure by H1 gamma 1. So again, we have gamma 1 in there, gamma 2 in here, and we'll have a third fluid, gamma 3. To go to point 2, we increase by gamma 1 H1. P2 equals P3, so I'm just going to rewrite that here to have it all in order. Then point 4, so I'm going from A, 1 to 2 to 3. Now I'm going to point 4 here. Then we need to decrease the pressure because we're going upwards by gamma 2 H2. And then point 5, let's call point 5 right here at the level of B. And we have another height here. Let's call it H3. So 0.5. We decrease by gamma 3 H3. It's gamma 3 over here, the third liquid. And then 5 is equal to B, right? Same fluid, same elevation. So P5 is equal to PB. And so you see now what we've done is actually just follow from point A to point B and just appropriately add or decrease pressure according to the differences in elevation each step of the way. This is how you solve the manometer problems in general. Now we can find the final answer, which is pressure at A plus the pressure difference from 1 to 2, gamma 1 H1, minus the pressure difference from 3 to 4, gamma 2 H2, and minus the pressure difference from 4 to 5, gamma 3 H3, is equal to the pressure at B. And so now the pressure difference P A minus PB is equal to, move everything to the other side, and we have gamma 2 H2 plus gamma 3 H3 minus gamma 1 H1. Again, we could have that the gauge fluid is much heavier, and we could find that if these other ones are gases, we can basically neglect all of these guys. We can neglect this and make this approximately equal if gamma 3 and gamma 1 small, for the case of gases. Because it could be just, you can actually do a calculation in some exercises, so you see that it could be less than 1%, and you, for engineering purposes, might be content with an approximate result within 1%, and you can make your life easier by neglecting those points. But before you neglect anything, it's good to actually do the whole process so you understand how we've been able to reach that answer. This is a typical manometer situation. And the last one is the inclined tube manometer. It's the same as the previous one, exactly the same. The only difference is that this U-tube is now inclined a certain angle, and this is used to measure when you have very small pressure changes. So again, we have the same as the previous situation. We have a liquid here, gamma 1, another liquid here, gamma 2, another one here, gamma 3, and we want to calculate the pressure difference between point A and point B. And we go same as before. We have H1, and what we will do is we have an angle here, theta, and what we measure in the inclined manometer is going to be this length, L2, and we just need to incorporate the angle, because what matters is going to be the heights, but we will use, so you can see how this will give me the possibility of measuring very small differences in height, but since I'm looking at the length, if I put a ruler there, I can actually see it, with much more resolution. And so the difference here is, skipping right to the result, PA. We want to find PA minus PB, but we get it from PA plus, again, gamma 1 H1 minus gamma 2 L2 sine theta. This is the vertical distance H2 that we had before. Vertical distance between points 1 and, so I'm calling this one 1 here and 2 here. This is the vertical distance between points 1 and 2 minus gamma 3 H3 equals PB, and you can see now I can solve again for the PA. Now again, if fluids 1 and 2, no, so 1 and 3. So fluids, let me be more clear even. I missed, okay, what did I do? Fluids, sorry about that. Fluids in A and B are gases, then neglect the gamma 1 H1 term and the gamma 3 H3. I know what I did actually. So now we get PA minus PB equals simply the term that had gamma 2 L2 sine theta. Make sense? So you will use this quite a bit for your labs, and we will have some problems, some exercises in your homework with manometry, and with some exercises this will get very, you will get very good at this. So we'll take a break, but before that, I would like to introduce to you Rio Yakoda. Rio is a postdoctoral fellow here at Boston University, and he's going to be the guest lecturer for next Wednesday's class.